All right, this is our last lesson on new material for the year. Super exciting. So we're going to start with a problem you should be able to mostly do. Consider the differential equation dy dx equals 1 plus y over x. Find the particular solution to the differential equation with the initial condition f of negative 1 equals 1. And then in a minute, we'll do this together. We'll state the domain. But for now, go ahead and find the particular solution on your own. And hopefully you started by realizing we need the y's on the left. And so I'm going to rewrite this as 1 over y, 1 plus y times 1 over x. And I'm going to multiply the dx on the other side. And we see that we need to get the 1 plus y on the left side. And so we need to divide by 1 plus y. So we get 1 over 1 plus y dy equals 1 over x dx. On the left side, this is a u substitution. U equals 1 plus y, du equals the derivative of y is just 1 dy. And so this is going to be a natural log. This is 1 over u du. So natural log absolute value of y plus 1. I'm going to change it from 1 plus y to y plus 1. And dividing by 1 doesn't do anything, so it's not really going to change anything. Here we've got natural log absolute value of x plus c. And let's go ahead and plug in, this point is when x is negative 1, y is 1. So when y is 1, we get natural log of 2 equals natural log of, when x is negative 1, absolute value of negative 1 is 1 plus c, and natural log of 1 is 0. So c equals natural log of 2. Okay, and we'll plug that in. And we'll get natural log of absolute value of y plus 1 equals natural log of absolute value of x plus natural log of 2. And from here, we need to get y by itself by doing e to the power of both sides. And we have to remember that this is a binomial. And I hope we recognize that this is e to the natural log of absolute value of x times e to the natural log of 2, and that this will cancel out and just give us 2. So it becomes just absolute value of y plus 1 equals, and this is also going to cancel out. So we get 2 absolute value of x. Now, these are both absolute values, so we can't really tell exactly what's going on here. Because this will be positive or negative, and I see that the y value is 1, so the y value is above 0. So I know when I do this, this needs to be positive, but I think I still need the absolute value of x here because there's nothing that tells me a reason why it shouldn't be absolute value. So y equals 2, absolute value of x, minus 1. And so the question is, what is the domain? And is there a reason why I can't have any x values? It sure looks like the domain should be like, this would look like this. So this is what this graph looks like, right? Is there any reason I can't have all x values? And the answer is yes. We need to look back at the beginning. And at the very beginning, the slopes are going to be here, and we can't divide by 0. At x equals 0, the slope is undefined, right? Because you're dividing by 0. And so since x can't be 0, this slope field cannot cross x equals 0. And in fact, because it can't cross x equals 0, because there is no value defined here at this slope field, only one of these sides will exist. So we'll talk about this quite a bit here, where if you have a value where it's undefined or the slope is undefined, we'll only pick one of these sides. And we'll need to look back at the initial condition to decide which side we're going to be on. Negative 1, 1. That's our point. And since that's the point on our slope field, that is going to be where our solution is going to exist. And so our domain is actually going to be just x is less than 0. It looks like you could have x's to the right of 0, but because there is no x value at x equals 0, it'll only be to one side of it. The slopes will stop there. There will stop being a slope field, and so it'll just be x is less than 0. And if we want, we could actually put, since this is now just a one-sided function, we could put y equals 2x minus 1. Like, this is fine also, because it's only a one-sided thing. So when we're looking at domains, we're looking to see, is there any place either in the solution or the derivative where it's undefined? And so that's what we're doing there. All right, let's look at a new type of thing, some differential equation word problems. And I think you won't have too much trouble with this, although at first it might seem a little bit weird. The rate, when you see rate, you should think derivative. The rate at which your investment grows, again, this is a rate here, how much your investment is growing by, is proportional to, we'll talk to you about that in a second, the value of the investment. So this is the variable, right? The value of the investment is a variable. Could be like $5, $10, $1 million, right? It doesn't matter. The value of an investment is an amount. The rate at which the investment grows is going to be something like $5 per year, right? It's a rate. So it's a value per time. So this is a rate. And this is a relationship between the rate and the value of the investment. And that's just what we've been doing up here. We've had a rate that is equal to a variable. And so it's the setup of a differential equation. Now in this case it says is proportional to. And let's remember from Algebra 1, a long time ago, is proportional to is a direct relationship. So if something is proportional to something else, it's just multiplied by a constant. So proportional to something just means it's multiplied times that thing. There's a constant multiplied times that thing. And so in this case, the rate at which your investment grows, I'm going to call it di dt. Di dt, that's a rate, right? The rate at which your investment grows is proportional to, so it's equal to a constant times the thing it's proportional to, the value of the investment. And so I is our variable here, and you'll notice it'll show up on both sides, right? So here's our value of our investment. I'm going to call this I. The value of the investment is I. And the rate at which the investment grows is di dt, how much the investment is changing by. You'll notice that this variable will show up once as a rate and once as a variable. And if we really wanted to, we could change this to dy dt, but it's going to be the same thing, right? Like the i's, when we solve this, we're going to need all the i's on the left side and all the t's on the right side. So try to solve this real quick. Recognize that k is a constant here, not a variable. So hopefully what you started by doing was move the I to the left side. So you get 1 over I times di. You move the t's over to the right side, k dt. And notice that the variable here is t, time, right? K is a constant. So when we do the integral on both sides, the integral of 1 over I di is going to be natural log absolute value of I equals, this is just like a constant, it's like 5 dx, right? And the integral of 5 dx is just 5x. So this is kt plus c. The dt, the thing that gives me a derivative that's just going to be dt is t, right? And it's just multiplied by a constant. We do need the plus c there. And so this is the general equation, this is the general solution to the differential equation. Okay. Determine the particular solution given that you initially invest $1,000 and your investment grows to $1,500 after 10 years. Now, what we're looking for here is we want to find both K and C if we can. And so some of this is going to come down to our algebra 2. Oh, wait, this isn't the general solution, guys. I forgot to solve for I. Let me go ahead and do that. We can't solve for C yet because they didn't give us any particular information, but we can solve for I. We're going to do e to the power of both sides. Man, so embarrassing. E to the power of both sides. And so we'll get I equals, e to the c is just going to be some sort of c, right? So it's e to the kt times e to the c, but this is just a constant. It'll be some constant times e to the kt. So here is our equation. We don't know what c is and we don't know what k is. And c could actually be positive or negative, although, you know, in real world solutions where you're investing, it's going to be positive. Okay, determine the particular solution given that you initially invest $1,000 and your investment grows to $1,500 after 10 years. So you initially invest $1,000. This means when t equals 0, your investment is 1,000. So we should be able to find what c is based on this. Go ahead and do that. C is equal to what? Well, when you put in t is 0, it'll be e to the 0 power, which is just 1, until you get 1,000, which is I, the investment is 1,000, is equal to c times e to the 0 power, which is just 1. So c is 1,000, okay? So I'm going to substitute that back in and get I equals 1,000 e to the kt. And now this is an algebra 2 thing. If the investment grows to $1,500 after 10 years, so when t is 10, the investment is 1,500, we can find what k is now. You do need a calculator for this. So 1,500 equals 1,000 e to the k times 10. And we're going to solve for k. So we divide by 1,000 on both sides, so 1.5 equals e to the 10k. I just switched the order here, 10 times k. We need to do the natural log on both sides. And then we can divide by 10. I guess we don't need a calculator. We could have left it as natural log of 1.5 divided by 10. But let's go ahead and see what that decimal is. So natural log of 1.5 divided by 10 is 0.0405. This is a growth rate of 4%. It's growing by about 4% each year. So our particular solution is that I is equal to 1,000 e to the 0.041 or 0.04, you can put either one, t. This is the function that initially had $1,000, and you might remember from Algebra 2 that if you start with $1,000, that'll be what it's multiplying by. E to the 0.041 t, great, okay. And that will grow to $1,500 after 10 years. If you plug in 10, that'll be $1,500. Okay, how long will it take for your initial investment to double? This is really just an Algebra 2 problem. You can solve that from here. So if it doubles, your initial investment was 1,000, it needs to get up to $2,000. 0.041 t, we divide by 1,000, do the natural log on both sides, that'll cancel out the e. Oh wait, where'd my t go? And I'm going to divide by this. T equals, and I'm actually going to use this number from up here without rounding, so it's natural log of 2 divided by, and I'm going to press up to actually highlight that number and press enter so I can use the exact one. I don't want to round in the middle of a problem. So it'll be 17.095 years. So that makes sense, right? If it grew up to $1,500 after 10 years, it'll grow up to $2,000 after 17 years. I believe that. So that's what's going on there. All right. A new one, and you guys can try to find the equation here. What is the differential equation this represents? The growth rate for a population of fruit flies is proportional to the number present. So this is what I want you to write an equation based on. So write a differential equation based on this, okay? Hopefully you noticed the variable here is the number present. I'm gonna call this P. The number present or the population, and the growth rate of the population, how fast that population growing is dp dt. So we should get dp dt equals, it's proportional to, so it's going to be a constant times p. And again, we're looking for a relationship between p and t, so p and t. And it gives us more information now. So it says the initial population was 100 flies, and after 4 days there were 500 flies. So find the particular solution. What does p equal to? Hopefully, you started by solving the differential equation to find the general solution, right? So we can do 1 over p dp. We want to get all the p's on the left side. That's like our dy dx. We want the y's on the left side. Equals k dt. So we get the t's on the right side and the p's on the left side. And we do the integral on both sides. And so we'll get natural log absolute value of p equals kt plus c, just like before. In fact, it's like the exact same equation as it was last problem. And let's see, I guess I can solve for t here if I want. I can say the initial population was 100. So the initial population means when t equals 0, p is 100. So natural log of 100 equals 0 plus c, so c. Okay. So natural log of absolute value of p equals kt plus natural log of 100. This is a t. And I need to do e to the power of both sides. So absolute value of p equals, this is going to be e to the kt times e to the natural log of 100, which will cancel out, just give me 100. And this is either plus or minus, but I know the population is positive, so this will just be a positive 100 here. Okay, cool. So I've got p equals this. And now after 4 days, there were 500 flies. So when t equals 4, p equals 500. So let's find that. 500 equals 100 e to the k times 4. And guys, I could have done like I did before and just like found the general solution first and then solved for c. But I could solve for c earlier here because it gave me the initial condition right away. I'm going to divide by 100 and take the natural log of both sides to get rid of the e to the power of. So 4k. K is natural log of 5 divided by 4. Okay, so let's plug that in. I guess I'll change it to a decimal. Natural log of 5 divided by 4 is 0.402. So my solution is, I found what k is, p equals 100 e to the 0.402t. That is my expression for what p is equal to, and I used the initial conditions to find it. What will the population be after 10 days? Well, plug in 10 into this. 100 e to the, guys, don't use 0.402, use the exact number, times 10. We're putting in 10 for t. And I'm fine with you rounding to 3 decimal places. There's an argument to be made here that we should. We don't need to put the 0 at the end. The 99 rounds up, so 99 rounds up. But it's also fine to, when you're talking about populations, to round to the nearest whole number, because like for the number of flies, we might want a whole number answer there. But 3 decimal places is okay because they didn't tell us, and this is like what the model suggests. When will the population be 1,000 flies? So when will the population be 1,000 flies? We're going to put in 1,000 for here. 1,000 equals 100 e to the 0.402t divided by 100. And now we can take the natural log of both sides. Natural log of 10 equals 0.402t. And we can divide by 0.402. Natural log of 10 divided by, again, let's use that exact number. And it'll be t equals 5.723 days. Now, days we wouldn't round to the nearest whole number because you can have part of a day, and that makes sense. So anyway, there's some algebra 2 involved here that you might need to know. Okay, at time t equals 0, the drain of a hot tub is opened and the water flows out. Okay, so you pull out the drain and the water starts to go out. The rate at which the water flows out, is proportional to the square root of the volume, V, cubic feet of water left. Okay, write a differential equation for the rate that the water flows out from the tub. Try to do that. And hopefully you got that the variable here is volume, and so the rate is dV dt. So dV dt equals, it's proportional to, so a constant times, and it's proportional to the square root of the volume, so the square root of V. So that should be our differential equation. So solve this differential equation in terms of V and T. So again, we've got v and t and we want to solve it. So we want the t's on the right side. Hopefully you were able to do this. And we want the v's on the left side. So 1 over square root of v times k dt. So this is our separation of variables, all the v's on the left, all the t's on the right. Now here we need to do the integral of 1 over square root of v. I hope you recognize that this is a power rule. This is v to the negative 1/2 power. And so to do the integral, when we do the integral, we will raise the power by 1, so it'll be v to the 1/2 power, and we divide by the by 1/2. So dividing by 1/2 is multiplying by 2. Here this is kt plus c, and we need to solve for v. So it'll still have, it says it'll still have k and c in it, so that's fine. So I'm going to divide by 2. So this is square root of v. Square root of v equals kt plus c divided by 2. And to get rid of the square root, v is kt plus c divided by 2 squared. So that is v. Suppose that the hot tub initially, that means when t is 0, contains 196 feet cubed. We should notice this is a volume. And so that'll let us plug in to find like what the C is or something like that. And the drain first opened, the water flowed at 28 feet cubed per minute. So hopefully we recognize that this is a rate. This is dv dt, right? Feet cubed per minute. And when the drain is first open, that's also when t equals 0. So when the time is 0, dv dt is negative 28 because the water is flowing out, the volume is going down. Find the particular solution to the differential equation. Okay, so hopefully you put in when t equals 0, the volume is 196. So 196 equals when t is 0, we get 0 plus c divided by 2 squared. Let's take the square root of both sides. I think that's 14, but if you needed a calculator, it's not the worst thing in the world. It's plus or minus 14, but it's not going to contain negative 14 cubic feet of water. That doesn't make any sense. So c over 2, and then multiply by 2. So 28 equals c. So the initial condition is 28. That's the c. So I can put in 28 here. So v equals kt plus 28 divided by 2 squared. Let's see. Now, we also needed that dv dt when t equals 0 was negative 28. So where was our dv dt equation? We can use that up here. So negative 28 equals k times, we found that the initial, when t equals 0, so when t equals 0, dv dt is negative 28. But we also found that when t equals 0, v was 196. So because at t equals 0, v was 196. So we knew that. So we can plug in both the initial volume and the initial rate. So negative 28 equals k times, this is 14, and we can divide by 14 to get what k is. So k is negative 2. So we've got both k and c, and so v equals, what do we have here? Negative 2t, k was negative 2, plus 28 divided by 2 squared. We could leave it like that, but because they both divide by 2 really nicely, I think I'm going to do that. This would be the nicer way to leave it. Negative t plus 14 squared. If you really wanted to, you could square this binomial and get t squared minus 28t plus 196. That's also fine. So all of these are fine. These are all fine ways to leave it. From the initial time, how long will it take to empty the hot tub? When will the hot tub be empty? So we're looking for what the time is equal to, and we want the hot tub to be empty. That means the volume will be 0. So we can plug in 0 into here or here or here. I think I'm going to use this one. This one looks easiest. 0 equals negative t plus 14 squared, and I'm going to solve this. Take the square root of both sides, move the 14 to the other side, divide by negative 1, t equals 14. And what is this measured in? Minutes. This is in minutes. So 14 minutes, the hot tub will be empty. So guys, setting up a differential equation involves relating a rate, which is what all differential equations have been. There'll be a rate of something compared to that thing. And sometimes it's directly to that thing, sometimes it's to the square root of that thing or the thing squared. But these are pretty similar problems. You'll get a little bit of practice with it before it'll be on our test review. But that's it, guys. That's all the new stuff for the year. You have now learned all the calculus that is on the AP exam for the year. We'll take our test on this unit, and then we will be doing review of all your stuff. So congratulations, you've made it through learning calculus, and I think you'll be shocked at how quickly some of the stuff you may have forgotten comes back to you. Have a good rest of your day.